start. So today I plan to do 3 things, and I'm not sure I will have time to do the third, but the third is the start of what I'll do tomorrow. So first I want to finish the computation of the crossing probabilities that I started yesterday. Then I want to say something about what happens at kappa equal to 8. And here we'll just tell you what happens, and I will not give you any proofs because it would take too much time. And then I will start looking at what is known as radial SLE. And this will continue tomorrow. So recall what we wanted to compute and what I stated yesterday. And I want to restate it because there was some normalization missing in the statement. And also because I want to just change the notation a little bit just to fit what is in the literature. So what we had was an SLE in the upper half plane. So SLE kappa, and I'm taking kappa between 4 and 8. So it started at 0, and what you do is you take 2 points, A and C, A on the left and C on the right, and you want to know the probability that the SLE curve, so you know it will have double points, you want the probability that this does this. So the probability that you touch to the right of C before you touch to the left of A. And as I argued yesterday, this corresponds to the crossing probability for interfaces if the SLE is the scaling limit of an interface. So what you should keep in mind is that this would correspond to Cardy's formula for percolation in a domain which is the upper half plane with 4 marked points on the boundary, which are A, 0, C, and infinity. So this essentially is the crossing probability between the interval here and the interval here. So touching here means exactly that in the underlying microscopic model, there would be a crossing between these 2 intervals on the boundary. So the theorem was this, that the probability that SLE kappa hits to the right of C before hitting to the left of A, so that this was exactly equal to some function of minus A over C minus A, where the f is explicit, so f of u is integral from 0 of u of dx over x1 minus x to the power 4 over kappa. So this is what I wrote, but it's not exactly true. So you need to put some normalization z kappa, and z kappa is what you need for f of 1 to be equal to 1. So z kappa is just the integral up to 0 up to 1. So it's integral from 0 to 1 of dx over x1 minus x to the power of 4 over kappa. So that's the statement, and the goal is first to show that this statement is true and to relate. So the goal is to prove the theorem and to relate to the percolation result. So from the course of Clément, you know that crossing probabilities for critical percolation on side percolation on a triangular lattice, they converge to something explicit as well, which is not given as an integral, but which is given in terms of one conformal map from the domain to an equilateral triangle. And I hope that I can convince you that there are just two different ways of writing the same thing. So first, how do you prove a formula like this? So it's a little bit similar to what we did when we looked at the transition at kappa equal to 4. So the main idea is to turn the problem into a question of stochastic analysis. So in the real life. So to take an a priori very geometric question and to turn it into some problem which is computing the probability of an event which says something about the behavior of a one-dimensional stochastic process. So here's the main idea. So here is A, here is 0, and here is B. I want to say whether the curve started here will touch to the right of C, to the right of C, before touching to the left of A. And to study that, I will look at the curve from the beginning and use the Markov property. So let's take T, which is positive, and think of it as being very small. So what you can look at is the behavior of the curve up to time t. So this is gamma t. And I'm taking t very small in such a way that I can be almost sure that by time t I have not touched to the left of A and I have not touched to the right of C. And I can take t very small. If you want to do it properly, you need to take a stopping time and ensure that this is almost sure that you don't touch outside of the interval before time t. But for the moment, let's assume that we know that at this time t, we cannot touch to the left of A or to the right of C. So what it means is that the first hitting time to the left of A or to the right of C happens after time t. And what I can do is I can condition the process by what we discover up to time t, and say the following, that, so I will put it here. So the probability of this event here, so C before A, this is the expected value of the conditional probability given what I discover by time t. So the expected probability of touching C before A given Ft. And Ft is just the sigma field discovered at time t in the filtration generated by the driving process. Okay, so this is just an equality. It's just saying that any probability is satisfying this, you can always condition and decondition. So what do we do now? We have this curve up to time t. We have a domain which is the complement of this curve. So we do always the same thing. We look at the conformal map GT. And this GT maps A to here GT of A. It maps C to GT of C. It maps the tip here to beta t. And it maps the future of the curve. So the green part of the curve here to the green part here. And by the conformal invariance and domain Markov property of SLE, the image here that you get, if you shift everything back to 0, it will be an SLE starting at 0. So just to make the picture fit in the board here, I will map by GT minus beta t. So this is mapped to gt of a minus beta t. This is mapped to 0. This is mapped to gt of c minus beta t. And then the future of the curve is mapped exactly to an SLE curve, which is independent of what I discovered by time t. So that's what we get by the domain Markov property. On the other hand, if you look at the event that this curve touches to the right of C before touching to the left of A, well, this is also mapped to something nice by the conformal map. It's exactly equivalent to saying that the green curve here touches to the right here before touching to the left here. So this conditional probability can be written as expectation of, so this conditional probability, it's the probability for the green curve, and it's exactly the probability that an SLE touches to the right of this, so gt of c minus beta t plus infinity before minus infinity up to this point, gt of a minus beta t. So this is the probability, and then you take the expectation. So obviously this depends on what you did by time t, because the location of these points depends on the beta up to time t. And then you take the expectation of that. So again, this is an equality up to the question of the possibility of touching outside by time t. So if you put a stopping time for which this is almost sure, this is an equality. Okay, so this is where we are at. We want to compute this probability to hit to the right of a point before hitting to the left of a point in H. And we write it in terms of itself, essentially. This is the same probability, except the location of the target points, A and C, is different in the new domain. So, first of all, so the remark I did yesterday is by scaling variance, so if you let phi of AC to be the probability that you hit C infinity before minus infinity A, whenever you take lambda positive, what you have is that phi of lambda A lambda C is equal to phi of AC. And that's because if you scale the SLE by a factor lambda, you get an SLE, and the event corresponding to this and corresponding to this are the image of each other by this scaling. So this probability has to be the same. So what this really means is that you can, for instance, look at lambda to be 1 over c, and this is phi of a over c 1, so it's a function of the ratio a over c. So really what it tells you is that there is a function f such that phi of AC can be written as this function of the ratio a over c. But to make the computation simpler, I will just write it in terms of this ratio minus a over c minus a. So of course, if you divide up and down by c, you get that this is in bijection with a over c. So you can define f so that the probability here in the statement of the theorem is exactly f of minus a over c minus a. So the existence of f is just from the scaling. And then if you restate this equality here in terms of f, what you get is that, so let's call this star. So star is equivalent now to, so on the left we have f of minus a over c minus a. And on the right we have the expectation of f of something. So it's the expectation of f of what? So it's minus the new a, and the new a is this. So what you get is beta t minus dt of a divided by the new c minus the new a, and the new c is this. So you see that the beta simplifies between the two sides, and you get gt of c minus gt of a. So that's what we get from the domain Markov property. So again, this is true as long as we know that the event that we want does not occur before the time t. So in fact, this would be true replacing t by any stopping time for which we are almost sure that you haven't touched to the left or to the right. But then this extends to a stopping time because all we did was use the domain Markov property, and this was true for any stopping time. So really what we get from this is the following, is that this process here inside the expectation has to be a local martingale. So the f of beta t minus gt of a over gt of c minus gt of a is a local martingale. And it's really local because you need to stop it whenever one of these two events occurs. So it's really what you want. That the image of this ratio by f is really a local martingale. So now the plan for the end of the proof is clear. It's that we want to write that this is a local martingale. We will assume that f is C2. Then we will apply the Ito formula to this to compute the variations of this f of this ratio. And we will write that the drift term should be identically 0. And so this is exactly saying that this is a local martingale. And this equation here, that's an ODE in F. So that's what I will do. I will do the computation without doing all the steps, but that's the overview of the computation. So from the fact that it's a local martingale, we'll get an ODE in F. And what we can do is we can solve this ODE in F to compute F. And to do that, we need boundary conditions. So to find the unique solution to this ODE satisfying the boundary condition that we have. So let's do it a little bit backwards. Let's start with the boundary condition. So recall we are looking at SLE for kappa bigger than 4. So we know that all these processes gt of a point minus beta t, they behave like Bessel processes up to a factor of square root of kappa, but they are Bessel processes. So we know that in addition to that, they have dimension which is less than 2, so they will touch 0 in finite time. And besides, we know that this will occur very quickly if you start very close. So if the point A is very close to 0, you are very likely to swallow it in very small time. So if A is very close to 0, then the probability to hit minus infinity A quickly is close to 1. So that's a bit informal, but you can make it exact by looking at the behavior of Bessel processes. And it will tell you that as A goes to 0, this probability goes to 1, and the probability that you hit C before A, it will go to 0 because you will touch A first in very small time. So what it tells you is that phi of AC, so this probability over there, goes to 0 as A goes to 0. So if you start close to the left end of the interval, you cannot essentially reach C before hitting to the left of A, because you will swallow A immediately. And similarly, phi of AC will go to 1 as C goes to 0. So this curve is for fixed C and this is for fixed A. So that's for the same reason. If you start very close to the endpoint on the right, you are very likely to touch on the right before going into any positive distance. So in particular, before you hit to the left of A. So this is telling you that the boundary condition for F, well, it comes from this. If A goes to 0, the argument of F goes to 0. So this can be written as F of 0 is equal to 0, and F of 1, which is the limit when C goes to 0 here, is equal to 1. So this is the boundary condition that we want. Okay, so this is taking care of this bit here. Now we need to apply Ito's formula to compute things. So the computation what do we know? We know that GT solves the Loewner equation. So we know that dt of GT of Z is 2 over GT of Z minus beta t. So this for any fixed point Z is given by the Loewner equation. And the other thing that we know is that the beta t is square root of kappa times the Brownian motion, so we have that d beta t is square root of kappa d beta. Okay, last thing, we want to set the computation in some manageable way. And what we saw was that the difference between the image of a fixed point and the driving process, this is a nice way to set the computation because it's essentially a Bessel process. So let's define AT to be this, so GT of A minus beta t. And CT to be GT of C minus beta t. So from the computation we did yesterday, these two things are Bessel processes up to a multiplicative factor of square root of kappa. So they are Markovian, and we know that, so we know how they behave. So the dAt is exactly 2 over AT dt minus square root of kappa dBt, and the same for C. So we know the increments of the AT and CT. And then we can rewrite this local martingale in terms of AT and CT, because on the top it's exactly minus AT, and on the bottom it's exactly CT minus AT. So the F of minus AT over CT minus AT is a local martingale. So now is the time you need to do a computation without making a mistake, and so I will just copy it from the notes. So the first natural step is to look at this process here and look at the increment. So if Zt is the minus AT over CT minus AT, then you can compute dZt. And this is just a rational fraction, so it's not so difficult. And then if you compute the increment of this, what you will find is this. So, okay, it's square root of kappa ddt over ct minus at. So this comes essentially from the beta term here, up there, plus 2 dt over ct minus at squared times 1 over zt minus 1 over 1 minus zt. So that is what comes out of the computation. It's just plugging the Loewner equation and the variations of beta into this and applying Ito's formula. So already you see that this zt and 1 minus zt, they will come up in the formula in the end. They are the same as the x and 1 minus x over there. So zt is not exactly Markovian because the ct minus at, that's close to being zt, but it's not a function of zt. Not a nice function of z. So what is natural to do is to make a time change. It will not change the fact that we have a local martingale if we make a time change. To get rid of these ct minus at and ct minus at squared here, so we want to introduce ds to be dt over ct minus at squared. And in this new time change, we will define zs tilde to be zt of s. So z as time s of t will be zt, so it's exactly a time change of the process. Well, it will act linearly in front of the dt term, and it will act according to the Brownian scaling in terms of the Brownian term, so it will take a square root of this, which is exactly this. So what we get is that the dzs tilde is square root of kappa d ds tilde, well, this is a Brownian motion, plus 2ds times 1 over zs tilde minus 1 over 1 minus zs tilde. And now we are happier because this will be a solution of a stochastic differential equation. It does, it has the Markov property because everything here is written in terms of the zs tilde. So we have this, and besides, we know that f of zs tilde has to be a local martingale. So again, we want to find a function f satisfying that f of zs tilde is a local martingale. And because we have this representation of f as the probability of an event, essentially, if we can find one function f making this into a local martingale, it will have to be the probability of the event that we want. So we'll do something like chemistry. We'll assume that it's C2, we'll compute it, we'll check that it's C2 and that it satisfies all the hypotheses, and then in particular, it was C2 to start with. It feels a little bit like cheating, but it's not cheating a lot. It works. So we can assume that f is C2. And we'll just have to check that it is actually C2 in the end. So, okay, we want this to be a local martingale, so we write the drift term here. And the drift term here comes from f prime times the drift term here. So what we get is this. Okay, let's call it z. So times twice 1 over z minus 1 over 1 minus z. So that's the drift term coming from the first order term in the Ito term. And then what you get is the Ito term, so it's a 1/2 f double prime of z times the kappa here. And this should be identically equal to 0. check I didn't miss a term somewhere here, but that's correct. Okay, so now we are out of the field of probability. We just have one ODE for the function f. Let's keep this here. And we can just rewrite it a little bit different. So what we want is the z, the 1 minus z, and the kappa over 4 to come out. So we just take these two here, and we end up with the equation which is kappa over 4 f double prime plus 1 over z minus 1 over 1 minus z f prime is equal to 0. That's a z. Okay, I hope I copied everything right. So this is the equation that you get on f prime. So this is a linear equation of the first order in f prime, so you can first solve in f prime, and what you get is, where you separate the term, you say that so f double prime divided by f prime is what? It's minus 1 over z minus 1 over 1 minus z divided by kappa over 4. So you take the integral and you get the log of f prime, and then you compute everything. And so this is just tedious computation from this point. And what we get is that the f of u, the f of z, has to be some antiderivative of the u over u times 1 minus u to the 4 over kappa. So this is what you will get, this 1 over this power of u of 1 minus u is what you will get as f prime by solving, by integrating this. So this 4 over kappa is this 4 over kappa here. So that's the solution, and then you need to take care of the boundary condition, and the boundary condition says that f of 0 is 0, so you have to integrate from 0, and f of 1 is 1, so this has to be a z, and f of 1 is 1, so you have to normalize by integral from 0 to 1, du over u times 1 minus u to the power 4 over kappa. And then this is indeed a C2 function in the open interval between 0 and 1, so everything fits together. So that's for the proof of the theorem, and again the important part is the overall arguments that from the statement of the probability and of the event that you are interested in, you apply the domain Markov property to get that something is a local martingale. And once you are there, it's just stochastic calculus, it's just computation. So that ends the proof of the theorem for the crossing probabilities. So we have the explicit formula, and this is what I wanted. So just one remark. What happens when kappa is equal to 6? So when kappa is equal to 6, what you have is that f of z is 1 over some normalizing factor times integral from 0 to z of du over u times 1 minus u to the power 2/3. So that's a nice formula. It's just an integral formula for the crossing probability. And on the other hand, we are expecting percolation to converge to one of the SLE kappas, and it will be kappa equal to 6, but I will just tell you why it will be kappa equal to 6, and that will come from the formula. The question is, how can we identify this function f in terms of a conformal map? So here, a priori, z is somewhere between 0 and 1. because that's in the statement of the theorem. What you plug inside f is this ratio between two lengths, so it's some real number between 0 and 1. So what you can notice here is that you can actually extend f to the upper half plane. And how do you do that? Well, first you extend this term here. So you first extend whatever you want to integrate. So it's the u times 1 minus u to the power minus 2/3. So a priori, the fractional power of u is not well defined in the whole complex plane because you have a singularity here at 0 and here at 1. But as long as your domain is simply connected and does not contain the singularities, it's fine to extend this into a holomorphic function in the whole upper half plane. So holomorphic on H. What you do is you write a differential equation, you integrate over path, and you say that what you get as a function over H does not depend on the short of the path. And this is true if the singularity is not in the domain, which is the case, if you want to extend that to H. So it makes sense to extend this power holomorphically on H. And then once you have this, you take an antiderivative here, and again, because H is simply connected, well, this extends f automatically to H. So then take the integral to z. And what you get is that f becomes a holomorphic function on the whole upper half plane. And besides, well, because of the whole construction, f prime of z is exactly this term here. So it's z times 1 minus z to the power minus 2/3. So what does it tell us? So let's do a picture. That will look a lot like the picture on the left here. Let's try to figure out what the image of H by f might be if we do this extension here. So this is H. This is 0, this is 1. And on the right, we have the interval 0, 1. And we know that f is increasing, it's continuous, it sends 0 to 0, 1 to 1. It's real on this interval 0, 1 because it's a probability. So it sends the interval 0, 1 to the interval 0, 1 here on the right. And if you want to reprove this, what you can do is you look at f prime of z. For z between 0 and 1, z times 1 minus z is a positive number, so this to the power minus 2/3 is also a positive number. So here the derivative of h is a positive real number. What about what happens on the left of 0? So on the left of 0, 1 minus z is positive, so it's not a problem, but you have a z to the minus 2/3. So here the f prime looks like z to the minus 2/3, and z is negative. So really what you have to do is to extend the z to the power 2/3 from here to here. And what it means is that you will take 2/3 of the angle. So what it will tell you is that z to the minus 2/3, actually it points in this direction. So it points in this direction. Now if you start from 0 and move to the left, and you want to look at the image of this half line, so look at the image of 0 up to minus infinity by f. So if you go from here to minus infinity, you move to the left, so the derivative is minus 1. And so the derivative of the image is minus the f prime here. So on the right, you will actually go in this direction, where this is pi over 3. It's just a computation of the angle, and the argument of f prime is constant in this half line. So the direction in which you are going is constant in the image of this half line by f, and it's exactly this pi over 3. So you go in this direction. So similarly here, the image of 1 plus infinity will go in this direction. And these have to meet at infinity because you can check that here, what you plug in here is integrable at infinity. So what you reach at infinity, it doesn't depend on the way you go there. So if you go to the left or to the right, you have to reach the same point. So it tells you that these have to meet somewhere here, which is automatically f of infinity. So that's it. We have a f which goes from h to the complex plane, but it sends the boundary of h to the boundary of this triangle, which is exactly the equilateral triangle. So by the argument principle that Clément explained just 1 hour ago, what this really means is that f is, when you extend it to h, it becomes a conformal map from h to the triangle, mapping 0 to 0, 1 to 1, and infinity to this point here. So that's e to the I pi over 3. And there is a unique such map because of the Riemann mapping theorem. So this is what we get from the integral representation here. We get that f is actually the trace on 0, 1 of this conformal map from h to the equilateral triangle. So in particular, if you want to compute this crossing probability, well, this here will be the f that you want. So that's the probability of the event. So that's the phi of AC. So it's exactly the same picture as in the calculation course. If you want to compute the crossing probability here, it will be conformally invariant, and you can read it here as the value of phi, so the crossing probability in an equilateral triangle between this and that is exactly this length. And that's exactly the statement of Caddy's formula. So the conclusion of this is that the crossing probability for an SLE6 is equal to the crossing probability for percolation. So just as an exercise, if you want to practice these kind of things, you can check for kappa different from 6. You can check what happens, if this can be done, if you can extend f, what is the domain on the image of f, things like this. And you will see exactly what happens. That essentially this is where the kappa less than 8 will be relevant, because that's where the integrand becomes non-integrable if you go to infinity. So you will see what happens, and for every value of kappa between 4 and 8, you will find one particular domain on the right which makes the crossing probability linear. So that's your exercise if you want to practice these kind of things. Any question? Okay, so that's the first point. The second thing is, and I will go very quickly on there, it's that so remember we saw that something interesting happens at kappa equal to 4. What we saw that was that if kappa is less or equal than 4, then gamma is a simple curve. And if kappa is bigger than 4, then gamma is not a simple curve. And if you take the union of the kts, the increasing union as t goes to infinity, this contains the real axis. And that was what came out of the story of Bessel processes. And in fact, this whole union is exactly h bar, and that's not much more difficult to prove, that you will hit any point in the upper half plane if you hit every point on the real line. So here is another theorem, which I will not prove, but I will give you some indication of how to convince yourself that it's true. It's the following. Whenever kappa is less than 8, gamma is kind of a nice curve. It has measure 0. It has Hausdorff dimension 1 plus kappa over 8. And sometimes it has double points if kappa is bigger than 4, sometimes it doesn't, but it's a curve like you want to draw a curve. It's not completely wild. And on the other hand, whenever kappa is bigger than 8, so kappa is onto. So whenever z is in h, there is a time at which gamma t is equal to z. So to sum up, there are exactly 3 phases for the SLE. There is a phase where kappa is less than 4. There is the case where kappa is strictly between 4 and 8. And the last one is for kappa bigger than 8. And what you see is that here you see a simple curve. It has no double point. It's really a Jordan curve. It's a little bit, well, it's fractal, but overall it's a nice topological curve. If kappa is between 4 and 8, this curve is still wiggly, but it touches itself and it touches the boundary. So it still has measure 0, which means that if you fix a point somewhere in the H, it will not be on the path, but almost surely it will be in one of these bubbles here. So what it means is that the complement of gamma is a countable union of open sets, and these open sets, their union is dense in the plane. So it looks like the Brennan path. If you saw pictures of the Brennan path, it's a curve which has measure 0, and the complement has an interesting structure. And the case kappa equal to 8 is something which is completely different and very difficult to draw, which is that it's oscillating like this, and it's covering all the points in the upper half plane. So here I drew it in a way which is too oriented. Of course, it's not directed, so it has overhangs like this, but it is going through every point in the upper half plane. So if you want to convince yourself that this is not completely absurd, you can actually compute, well, you can build one random curve that looks exactly like this, that is random, that is related to Brennan motion, and that is going through every point in the upper half plane. So just one example, which so you can take dt to be a Brennan motion, take LTX to be a local time of dt. So it's jointly continuous in t and x. It's increasing in t, and it increases only when the Brennan motion is at x. And what you can do is you take gamma t to be the points in the upper half plane which is of coordinates bt and lt at bt. And that's a very nice process because it's the fact that LT is strictly increasing whenever the Brennan is there is telling you that this will cover all the points, and besides it's a continuous curve, but the continuity of LT says that you will touch every point. So that's one example of a curve that kind of looks like SLE kappa for kappa bigger than 8. And somehow this is the natural definition of SLE for kappa equal to plus infinity. That's what you get if you rescale things properly and let kappa go to infinity. Okay, so just one idea of the proof. Of the fact that if kappa is bigger than 8, you go through every point. So there is a computation that is very similar to what I did here, but for the probability that gamma goes to the left of a point z. So in the picture, this is 0, this is z, and the event that you want is something like that. So, well, again, you can compute this as a function of the location of the point z. And it's some function of the argument of z. So as long as kappa is less than 8, this is a very nice function. It's again some integral representation in terms of the argument. It's non-trivial. It goes to 0 if the argument is here. It goes to 1 if the argument is here, because then it's difficult to sneak below the point z. But at kappa equal to 8, what you get is that this function becomes identically equal to 1/2. And what this means is that even if you take a point which is very close to the axis here, you still have probability 1/2 to go below it. So what it means is that if you want a point, or if you want to show that a point is on the curve, well, whatever the curve does for time t, even if this point is marked very far away so it would not be touched by the curve, the future of the curve still has probability 1/2 to go below. So this is the kind of computation that will tell you that something like this happens at kappa equal to 8, that some events that should have a very small probability, like touching a given point on the axis, in fact they turn out to have a positive probability, or probability 1. So here, for instance, letting this point go to the axis, because it's constantly equal to 1/2, what you will get is that the probability that the curve actually touches this point on the axis is equal to 1. So if you touch every point on the axis, then it's not difficult to convince yourself that you actually touch all the points in the upper half. So that's not the actual proof, but that's one way to convince yourself that kappa equal to 8 is special in the computation. Okay, I kind of said what happened at kappa equal to 8. I have no time today to speak about radial SLE, so that will be the program for tomorrow. So thanks. Any questions?